This time we're actually going to be able to do a little work that I hope will give you a good idea of why it is that at least low-density parity check codes work, and even broader classes of capacity-achieving codes. But we're going to limit ourselves to a week so that we can say something next week about everything we've been talking about is binary codes for the power-limited additive white Gaussian noise channel. We've completely left aside codes for the bandwidth-limited channel, where clearly we're going to have to talk about non-binary codes of some kind. So next week I'll give you a very rushed overview of that kind of code. And it's my intention, by the way, that that last week you'll not be held responsible for on the exam, so that we can have a nice, pleasant week without worrying about whether we're responsible for it or not. And the last homework set, I will prepare a homework set on the bandwidth-limited type codes on Wednesday. I'll hand it out, but I won't expect you to give it back. It's good to do it. I'll hand out solutions on the final day of the exam. Okay, so any questions about where we are, what we're doing? All right, let's get into it. We've been building up to this for a while. First we did Trellis representations of block codes as a warm-up for codes on graphs. We found that some of the things we discovered about trellises were important, particularly in the context of the cut set bound. The cut set bound says where you have a cut set, the complexity at that point must be at least as great as that of a trellis diagram, which divides the two parts of the code into two halves in the past and future in the same way. And from that, we concluded that we were going to need cycles because we'd already proved back in Chapter 10 that trellis complexity needed to go up exponentially with block length, at least for codes that maintained a non-zero relative minimum distance as well as a non-zero relative rate. So we're going to need cycles in our graph, we think, to get to capacity. Chapter 12 was a fairly short chapter introducing the sum product algorithm. I believe that you don't really understand the sum product algorithm until you do it once. So that's on this week's homework. You will do it once for a very simple case, and then I think you'll understand it. And we developed the sum product algorithm for cycle-free graphs, where it's a theorem that the sum product algorithm does APP decoding for every variable in any cycle-free graph in a very systematic and efficient way. It's a finite and exact algorithm in that case. It takes a number of steps approximately equal to the diameter of the graph, and when it's finished, you have the exact APPs everywhere. Okay, but we really want to have a decoding algorithm for graphs with cycles. Having developed the sum product decoding algorithm, we see that it has a nice simple update rule at each computation node. It's a local kind of algorithm. Why don't we just let her rip, start it off, and see how it does? And in our case, we can make that work by designing graphs that have, in particular, very large girths, such that the graph looks, the term of art is locally tree-like. In the neighborhood of any node, if you go out some fixed diameter from that node, you won't run into any repetition. So locally, the graph looks like a tree. And we're going to ultimately be looking at asymptotically long codes, so we'll be able to make that locally tree-like assumption hold for as far out as we need to. Other disciplines are not so fortunate to be able to do that. Okay, so in this chapter, we're finally going to get to capacity approaching codes. I'm first just going to mention a couple of classes of codes, the most famous and important ones, show you what their graphs look like. From that, you will know everything up to schedule, what their sum product decoding algorithm should be. I'll tell you what the conventional schedules for decoding these graphs with cycles are, and that'll be an introduction. And then we'll get into actual analysis, in particular for low-density parity check codes, which are really the simplest of these codes and therefore the most amenable to analysis. And we'll see that under the locally tree-like assumption, we can do an exact analysis, first on the binary erasure channel, and then I'll at least discuss what's involved on more general channels where we can do a fairly precise analysis. All right, so that's where we're going in Chapter 13. Questions, comments? Okay, so let's talk about low-density parity check codes. These codes have a fascinating history. They were invented by Professor Gallagher in his doctoral thesis in 1961. He was a student of Peter Elias. What people were doing at MIT then was trying to figure out ways to actually build codes that get to capacity. At MIT, the emphasis was on so-called probabilistic codes, namely ones that had sort of the random-like elements that Shannon basically prescribes. People here were not so interested in the algebraic codes. And Gallagher basically had the idea that if you take a code, you can describe it by a generator matrix or a parity check matrix. If you make a sparse generator matrix, that's not going to be any good, a random sparse generator matrix, because a sparse generator matrix will naturally have some low-weight code words in it. If the rows are sparse, they'll have low minimum distance. But maybe if we make the parity check matrix sparse, very few ones in the parity check matrix, we can still get a code that's quasi-random. And therefore, we can hope that the codes, as they get long, will come close to doing what Shannon said random codes should easily be able to do. The amazing thing about Shannon's proof was he showed that, you pick any code out of a hat and it's highly likely to be good. So basically, Gallagher was trying to replicate that, and he came up with the idea of sparse or low-density parity check matrices, and was able to prove quite a few things about them, that they couldn't quite get to capacity the way he formulated them, but that they could get very close. They had a threshold a little bit below capacity. He came up with the APP decoding algorithm for them, which is probably the first instance of the sum product algorithm in any literature, certainly the first that I'm aware of. And he simulated them. At that time, what MIT had was over in Building 26 on the first floor, where I think there's a library now. It sticks out into the adjacent parking lot. That room was full of IBM equipment, 7090 computer. And there were people in white coats who tended all that equipment. And by running that computer for hours, he was able to simulate low-density parity check codes down to an error probability of about 10 to the minus fourth. And he showed that he could get down to 10 to the minus fourth pretty close to capacity. I don't remember exactly how close, but it was enough to be convincing. So actually in 1962, there was a little company formed called Codex Corporation. It was formed by, it was what we would now call a startup. Back then there was no tradition of startups. And it was basically founded to exploit Gallagher's patents, which he took out on low-density parity check codes, and Jim Massey's patents on threshold decoding, which is an extremely simple decoding technique that we haven't even talked about, very low complexity. And I joined that company in 1965 when I finished my thesis, and I was director of research and advanced product planning, and I can assure you that in the 20 years that those patents lived, we'd never considered once using Gallagher's low-density parity check codes, because they were obviously far too complicated, all right, for the technology of the 60s and 70s. We didn't have rooms full of computers to decode them. And more generally, in the community, they were pretty completely forgotten about. You can find, there's a key paper by Michael Tanner in 1981, where he that's the founding paper for the field of codes on graphs. He puts it all into a codes on graphs context, develops all the basic results. It's a great paper. It, too, was forgotten about. And the whole thing was pretty much forgotten about by us until other people outside the community rediscovered it right after turbo codes were invented. Turbo codes were first presented in 1993 at the ICC in Geneva. They had actually been invented some 4 or 5 years before that by Claude Barroux in France. And nobody could believe how good the performance was. This guy is not even a communications guy. He must have made a 3 dB mistake, you know. He didn't divide by 2 somewhere. He showed you can get within about a dB of capacity with 2 simple codes, and we'll see that in a second. But sure enough, people went and verified that these codes worked the way he said they did, and all of a sudden there was an explosion of interest. And low-density parity check codes were rediscovered by a couple of people, notably David Mackay, who he also was a physicist like Barroux in England, and but he had an interest in information theory. At least he was trying to solve the right problem. And he had sort of similar ideas to what Gallagher had had, and he simulated them. By now you can simulate these codes on a desktop computer, and found that they got within a dB of capacity and so forth. And so then we were off to the races, and the whole paradigm of coding changed. But it certainly is an embarrassment to those of us who were faithfully in the field for 30, 35 years. You know, why didn't it occur to us that by the 90s technology was far enough advanced that we could go back and look at what Gallagher did and realize that these were actually pretty good codes and now implementable. So I think that's a nice story. It's kind of humbling to those of us in the field. On the other hand, we can say that, geez, Gallagher did it back in 1960. What's the big deal about turbo codes? So it depends what perspective you take. All right. I never know whether I should tell a lot of stories or not so many stories in this class. If you like more stories, just ask. Anyone have any questions at this point? All right, low-density parity check codes. Gallagher, 1961, forgotten until 1995, rediscovered by David Mackay, Nicholas Wiberg, and others. And this is what they look like. The basic idea is we have a parity check representation of a code, a long code. So the code is the set of all y such that yht equals 0. Okay. And that's standard. And the idea now is that this parity check matrix should be low density or sparse. All right. In fact, the number of ones in it, it's a matrix, so that you would think a random matrix of zeros and ones, n minus k by n matrix, would have a number of ones that goes up as n squared. As n becomes large, let's make sure that the number of ones only goes up linearly with n as the block length n becomes large. All right. So a sparse h means number of ones linear with n. And we'll see that implies that the complexity of the graph is linear with n. It has, the ones are going to correspond to the edges in the graph, and we'll have a linear number of edges, also a linear number of nodes, vertices. Okay, in general, what does a code like this look like? We have y0, y1 through, what does its graph look like, I should say? Yn minus 1. And then, so we're going to have n symbols, which in normal graphs we write as equals nodes. And over here we're going to have n minus k, a lesser number of constraints or checks, which in our notation we've been writing like this. And we're going to have an edge for each one in here. You can easily see that every one in the parity check matrix ensures that it says that one of the symbols participates in one of the checks. And therefore the number of edges is equal to the number of ones. So this is equal number of edges in graph. Not counting these little half edges out over here again. So, there's some random number of edges. We won't have them go to the same place. But this also is only linear with n here. And in fact, let's choose these edges. These edges are like a telephone switchboard. It's just a giant plug board where everything that goes out here you can consider going into a socket. So let's draw, for instance, for a regular code, let's draw the same number of sockets going out for each of the symbols. Each symbol is going to participate in the same number of checks. Each one is going to have the same degree. So that's why in graph terms it's regular. Each one of these checks, we're also going to say has the same degree. So this was basically the way Gallagher constructed codes. Regular, we'll later see if there's an advantage to making these somewhat irregular, these degree distributions. But this is certainly the simplest case. And then, all right, how do we make a random parity check code? So we're going to specify n minus k. We're going to specify these degrees. So that's not random. But we'll connect the edges through a big switchboard, which is denoted by pi, which stands for permutation. This is basically just a permutation. We've got to have the same number of sockets on this side as on this side, and this is just a reordering of these sockets. That's what a telephone switchboard does. Or it's very often in the literature called an interleaver, but probably permutation would have been a better word. All right, so one way of doing it is just to take this edge here, this socket here, and at random we have, let's say, E for a number of edges, E sockets over here, and just pick one of those E sockets at random. Take the next one and take the E minus 1 that are left and connect that to one of the E minus 1 at random. So this will give you one of the E factorial permutations of E objects, and it'll give you one of them equiprobably. So we're basically talking about an equiprobable distribution over all possible permutations of E elements. All right, so we consider all these are equally likely when we come to our analysis. This is why these codes are called probabilistic. We set up some elements of their structure, but then let others be chosen randomly. Clearly, it's not going to matter for the complexity of the decoding algorithm how this is done. It might have something to do with the performance of the decoding algorithm, but any decoding algorithm is going to work the same way. It's just a matter of when you send a message in here, where does it come out here, or vice versa. So it doesn't really affect complexity. Okay, let's see. There has to be some relation between the left degree d lambda and the right degree d rho here in order that we have the same number of edges on each side. We have E equals n times d lambda, if we look at the left side, but it's also equal to n minus k times the degree on the right side. Again, I'm only counting the internal degree here and leaving aside the external guy. And this gives us the following relationship, that n minus k over n is equal to d lambda over d rho, or equivalently, this is 1 minus the rate of the code, or we can write rate equals 1 minus d lambda over d rho. So that by deciding what left degree and what right degree to have, we're basically enforcing this relationship, which comes out as the rate of the code. For instance, the choice that we're going to talk about throughout is we're going to take a left degree equal to 3, right degree equal to 6, as I drew it. If you do that, then you're going to get a code of nominal rate 1/2. It's only nominal rate because what could happen here? When I choose, I'm basically choosing a random parity check matrix, and there's nothing that ensures that all of the rows of this parity check matrix are going to be independent. So I could have fewer than n minus k independent rows in the matrix, which would actually mean the rate would be higher than my design rate, my nominal rate. In fact, you can ignore this possibility. It doesn't, it's very low probability, even if you choose it at random. If it does happen, people are going to forget about the dependent row and pick another independent row. So I won't make a big deal. We'll just call this the rate. Okay, so if this were 3 here but only 4 here, then we would have a rate 1/4 code. We would only be able to have, we'd have to have 3/4 as many checks as we have symbols in order for everything to add up. Okay? So that's really basically it. Let's just specify the degrees on the left, the degree on the right, pick our permutation at random. We've designed a low density, pick n or e. We've designed a low density parity check code. And now how do we decode it? Well, we use the sum product algorithm. We've got a code on a graph. In fact, it's a very simple graph. Notice its characteristic. It's, again, just got equality nodes and zero-sum nodes, or check nodes. These are really the simplest codes. We can more generally have more elaborate codes here. That's one of the things Tanner did in his 1981 paper. But this is very simple. All of our internal variables are binary. I, for one, thought that it would be necessary to go beyond binary internal variables in order to get to capacity, but that proved not to be the case. Really, this structure is all you need to get to capacity, it turns out, except for one thing. You need to make these degrees irregular. And for the most part, you only need to make the left degrees irregular. So we'll get far enough to see why that is going to do the trick. But right now we're talking about the decoding algorithm. So the decoding algorithm is pretty much what you would think, I would hope, now that you've seen sum product decoding. You receive something on each of these lines, depending what the channel is. If it's an additive white Gaussian noise channel, you get a real number received vector that gives you some intrinsic information about the relative likelihoods of 0 and 1 on each of these lines. So each of these points, you get an ingoing message based on what you receive. At a repetition node, that message is simply propagated. If you look at the equations of the sum product algorithm, repetition nodes just propagate what they receive at one terminal on all the output terminals. All the all the D-1 terminals are determined by one terminal. So we get the same thing going as an output message. This very often is drawn as Tanner graph. In that case, all we have here is symbols, and it's natural to just take the likelihoods of the symbols and send them out. So we haven't done anything more than that. Okay, these messages all arrive here as incoming messages from various far and distant lands. And based on, to find the outgoing message, say on this line here, what's our rule? Our rule is to take the incoming messages on all D-1 of these nodes and combine their likelihoods according to which of these is consistent with a zero output here, and which of these is consistent with a 1 going out here. We get a bunch of weights for 0 and a bunch of weights for 1. We add them all up, and that gives us now a recomputed likelihood, a message consisting of probability of 0 given what we've seen so far and probability of 1 given what we've seen so far, that now goes out. Hopefully that's got some improved information in it now coming from all different parts of the graph, extrinsic. So this eventually will come back somewhere, say here, and similarly on all the other lines. And now this will give you additional information. You combine these, and now what you have coming out here is a combination of what you had coming in here, which was originally a state of complete ignorance. But now you combine these, you get more information going out, and so forth. So you iterate. You basically do a left side iteration, then a right side iteration, left side iteration, right side iteration. Hopefully the quality of your APP vectors is continually increasing during this. You're somehow incorporating more and more information. You're hopefully converging. And so you just keep going back and forth. In low-density parity check codes, you can do this typically 100 times, 200 times. It's a very simple calculation. You can do it a lot. So you do that. When do you stop? A very popular stopping rule is to stop as soon as you've got, if you made hard decisions on the basis of all these messages, that would give you binary values. And if all those binary values check at all these places, then that's a code word, or that's a trajectory that's consistent with a code word. Basically, everything that's over here then has to be a code word. So whenever all the checks check, just based on hard decisions, you stop. So if there's very little noise to start with, this can happen very quickly and terminate the calculation well short. Or you have some maximum number of iterations you're going to allow yourself. If you go 200 iterations and these things still don't check, probably you would say, this, I've detected a decoding error. One characteristic of low-density parity check codes is they tend to have good minimum distance. They tend to have a minimum distance that's sort of what you would get in a random-like code, which goes up linearly with the block length. So for a rate 1/2 of code of length 1,000, a random code would have minimum distance about 110, and a low-density parity check code would typically have, a large, maybe not 110, but a large minimum distance, unless you were just unlucky. So the probability of your actually converging to an incorrect code word is tiny. You don't actually make decoding errors. All of your errors are detectable, which is a nice systems advantage some of the time for low-density parity check codes. Yes?
So if a conversion to one code word, it's possible that if you add more iteration, it converts to another code word.
Possible in principle, but extraordinarily improbable. All right. And once you've converged to a code word, basically you've got all of the messages lined up in the same way. It's like a piece of iron ore where you've got all the magnets going in the same direction. What is there in that that's going to cause them to flip? All right, there's no impetus for any of these to. They'll tend to get more and more convinced that what they're doing is right. They'll reinforce each other. All right, so as a practical matter, I don't think it would ever, once it's the kind of landscape of these codes is that there's large areas of the parameters where it doesn't tell you to go in any particular direction, and then there are deep wells around code words. So typically the decoding algorithm is kind of wandering around in the desert here, but then once it gets into a well, it goes boom, down to the bottom of that well. And once it's down here, it's extremely unlikely that it'll spontaneously work itself out and come back over here again. And there are powerful basins of attraction here, which is another reason why, it's when we design the code, we're basically designing this landscape, and we can design it to, when it starts to converge, it really converges fast. That's why some classes of these codes are called tornado codes. They wander for a while, and then when they get the idea, boom, everything checks very quickly. Yes?
The schedule of the decoding algorithm here.
Mm-hmm.
So you compute the, so at each zero-sum node, there's one message that arrives, and then you've shown that you calculate one of the messages that go back. So do you calculate all of the messages that go back from each zero-sum node first and then propagate them back to the...
Yes, correct. I'm sorry. We not only calculate this one, but at the same time we calculate every other one, all E of them. Okay, each one of these is based on the D row minus 1 other inputs. All right, so it ignores the message that's coming in on that particular edge. It uses all the other messages to give an extrinsic message going out, which you could combine back here or here, the same thing, to give you your best overall APP right now from your right-going and your left-going messages. But you don't. You now use this new information in your next round over here. And the same thing on this side. You always compute one on the basis of all of the others. And the initialization is that initially you have no information coming this way. You can represent that by an APP vector that's 1/2, 1/2. Probability 1 is 0 is 1/2. Probability of 0 is 1/2. Any other questions? Okay, so that's how it works, and it works great. And as we'll see, even with regular codes, you can get within added white Gaussian noise channel terms. You can get within about a dB and a half of capacity, and merely by making these degree distributions irregular, this is how Se-Young Chung got the results that I showed, I think, in Chapter 1, where you get within 0.04 dB of white Gaussian noise capacity, and that's it. So we knew how to get to capacity since 1961 almost. We just didn't realize it. Yeah.
Is it LDPC regular, you get stuck at a certain gap, or?
I'm sorry, I missed.
With regular LDPC, you get stuck at a certain gap, or?
With regular LDPC, there's a threshold below which the algorithm works, above which the algorithm doesn't work, as we'll see shortly. And the threshold is not capacity; it's somewhat below capacity. By going to irregular, you can make that threshold as close to capacity as you like. You can never make it equal to capacity. All right, so let's talk about turbo codes. None of these ideas is very difficult, which is, again, humbling to those of us in the community who failed to think of them for 35 years. I really hope some historian of science someday does a nice job on culture and why some people were blind to this and some people saw it and so forth. Okay, so this is Baru, Lavia, and Thidimashima, which I always have problems spelling, in 1993. And their idea was pretty simple, too. Their idea is based on two rate 1/2 convolutional codes. So let me use notation. We have a certain U of D, which is a set of information bits. Okay, and to make a rate 1/2 convolutional code, all I have to do is pass that through a certain G of D. So I'm saying my generator matrix for the convolutional code is 1 and G of D. That'll make a rate 1/2 code. And this, let me call that a parity bit sequence occurring at the same rate as the information bit sequence. Okay? Easy enough. Now, let me take the same information bit sequence and let me put it through a large permutation, which again I'll represent by pi. And I want you to think of this as taking a 1,000-bit block and mixing it all up or something like that. Or actually it's better to use a so-called convolutional permutation, which is kind of stream-based, continuous, the same way the convolutional codes are. All right, but it's basically the same sequence permuted. And let's also put that through another G prime of D, which very often is G of D, so I'll just call that G of D again. And this is second parity bit sequence. And this all together I will call a rate 1/3 code. For every one information bit in, there are 3 information bits out. Same sense as convolutional. All right. So the second code, G prime of D, is 1 G prime of D. And the interesting thing is that these codes don't need to be very complicated. One thing they realized is they do want this to be a recursive code. In other words, G of D should look like N of D over D of D. And one particular purpose of that is that so a single information bit will ring forever. The impulse response to a single information bit is infinite. It takes at least 2, and you can prove to yourself there's always some sequence of length 2 in order to get a finite number of parity bits, a finite number of non-zero parity bits out of here. And then when those 2 bits are permuted, they're going to come up in totally different places, so they're going to look like 2 individual information bits down here, and therefore they're going to ring for a very long time. The basic idea is you don't want an information sequence which gives you a short code word out of here and a short code word out of here. And making it recursive, have feedback is what that means, is what you need to do to prevent that. Also gives you better codes, but I don't think that's really why. You know, if you have G of D over N of D, this is going to be equivalent to the code we're multiplying to the non-recursive feedback-free code, which is D of D, N of D, right? We worked all that out. You can just, it's equivalent to the code where you multiply through by the denominator. And so you get the same code with D of D, N of D, but you don't want to do that because you are concerned here about the input-output relationship between input bits and the encoded bits. All right, and you want the information bit sequence to come through by itself because it's going to be reused. You want the information bit sequence to be in common between these two. That's going to be the link when we decode these codes. We're going to send basically the messages concerning the information bit sequence is what's going to go back and forth between the two codes. All right, do you get the setup here? I'll give you a very different perspective on it by drawing the graph of this code. I mean, this is a graph of the code, but it's not the one we want. Let's draw the graph of this code. So, turbo code graph. I'll draw a normal graph, but again, if you like to do it as a Tanner style, be my guest. All right, this first code, let me do this in 2 steps. First of all, a rate 1/2 code graph. So for one of these codes, what does it look like? It's the Trellis graph, which in the normal graph picture is a very simple chain graph. It looks like this. Here's the information sequence. Here are the states. I say these might be simple codes. These are typically 4 to 16 states. So 2 to 4 bits of state information, not very complicated. So this is what it looks like. We get one of these for each. This is the branch constraint for each unit of time. This would be Y0, Y1, Y2, Y3. You get 2 bits out per each unit of time. And in this case, one of these is actually the input at that time, U0, U2. Well, we could adopt some other indexing scheme, but it's systematic, so we can think of these as the inputs, sort of driving an output. So maybe a better way to do this is, an alternative way to do it is like this. But it's all the same thing, right? It's what you've already seen. So I just want you to get used to this way of writing the trellis, the graph of a trellis of a rate 1/2 systematic convolutional code. Here are these systematic bits, which are both inputs and ultimately outputs onto the channel. These are the parity bits, which are only output onto the channel. All right, and these are the branch constraints for each time. And these are the state spaces for each time. Okay, so that I can always draw that way. All right, now up here, I really have 2 of these codes, possibly identical. And what's the connection between them? The connection between them is that they have the same information bits in some random order, some pseudo-random interleaved order. So I draw a graph of that. Again, I'm going to focus on the interleaver, make it nice and big now. There's always going to be a big interleaver in the center of all our charts. This is always the random-like element. Now let me draw my first convolutional code over here. The parity check bits, I'm just going to tilt this on its side. I'm going to put the parity bits on this side, the first parity sequence. So now this is running in time either up to down or down to up. I don't care. So forth, down to here, etc. Dot, 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 dot. And I'll put the information bits over here, and I'm going to do it in this way. The information bits are first of all used in this code. So I have a little equality. So these are going to be my information bits. But then they're going to go through this permutation and also be used in another code over on the right side. Is this clear? So this is everything up to here. I'm about to go into the interleaver. Stop me with questions if anything is mysterious about this. Okay, after some huge permutation, they come out over here. And now these are information bits that go into another identical trellis, or could be identical. So we have a trellis over on this side that's connected to one parity bit and one information bit. It's another rate 1/2 trellis. This is parity bits. These are, again, info bits. Same information bit sequence, but drastically permuted. Is that clear? So again, this is the same idea of a switchboard with sockets. We have the same number of sockets on the left side and on the right side, and we make a huge permutation that ties one to the other. It's only edges in here. Notice there's no computation that ever takes place in the interleaver. This is, again, it's purely edges, purely sending messages through here. So the analogy of a switchboard is a very good one, even though we don't have switchboards anymore. Maybe some of you don't even know what a telephone switchboard is. It's a quaint but apt analogy. All right, so this is the normal graph of a turbo code. And you see I've drawn it to emphasize its commonality with low-density parity check code. The biggest element is this big interleaver in here, and that's the key to the thing working well. All right, so how would we apply the sum product algorithm to this code? What would our decoding schedule be? In this case, when we observe the channel, we get messages in all these places. So we get intrinsic information coming in for all the external symbols. Okay. First step might be to okay, that's first step. We can, in the same way, this is just a distribution node when originally all else is ignorance. So these same messages just propagate out here, and if we like, we can get them out over here. And all of these are available too. Okay, somebody else. What's the next step? Somebody was just about to say it. Be bold, somebody.
Convolutional.
Excuse me?
The Trellis decoding.
Trellis decoding, right. If we forget about that side and just look at what the sum product algorithm does over here, we're doing the sum product algorithm on a trellis, the BCJR algorithm. So given all these messages, we do our backward-forward algorithm, alphas and betas, eventually epsilons, extrinsic information coming out on all nodes, there, and so forth. And that requires going up and down the whole trellis. If this is a 1,000-bit block, as it often is, or larger, it means going from top to bottom through the whole block and doing one sweep of a BCJR algorithm through that block, which will generate a bunch of extrinsic information over here. Okay, now we have more over here. We still got the same intrinsic information coming in here, but now we can take this new extrinsic information and combine it with this intrinsic information and hopefully get an improved, higher quality information, because we've incorporated all the information from all these received symbols on this side, and we send that over here. If you think of it in signal-to-noise ratio terms, as some people do, you hopefully have improved the signal-to-noise ratio in your information that's coming over. It's as though you received these bits over a higher quality channel. All right, they tell you more about the information bits than you got just from looking at the raw data from the channel. All right, that's basically where turbo comes from. You then do BCJR over here using this improved intrinsic information. Of course, the parity information hasn't improved. You might think of ways to improve this too, but this was the basic scheme. It works just fine. You come over here, you then do a complete sweep through 1,000 bits or whatever, and you develop outgoing messages here, which again, let's hope we've improved the signal-noise ratio a little bit more, that these are even more informative about the input bits. And they come back, and now with this further improved information, we can sweep through here again. That's where the turbo comes from. You keep recycling the information from left to right, from right to left, and hopefully you build up power, you lower the signal-noise ratio each time. Yes?
Here, it looks like if you are decoding on this side, and then you do the other side, it's kind of iterative. But why can't you? Because on this side, actually, the information bit is just interleaved version of the other side. Why don't you do it in parallel and send it in parallel and then do it again?
So a good question. You certainly could. I suspect that so after you've done it twice, you basically processed all the same things as this thing does in one iteration. You've spent twice as much effort. The question is your information, is now the quality of your information any better? And I haven't done this myself, but I suspect people in the business did this, and they found they didn't get enough improvement to make up for the additional computation. But that's an alternative that you could reasonably try.
The reason I say that is because if you do that way, that means, for the second decoding process of the left side, the information is very fresh because this is a brand new information. If you do this and this and this, it looks like there is kind of propagation of the same information to itself.
Well, there certainly is. There are certainly cycles in this graph.
Yeah. But if you do that, then there's.
Okay. Well, these are great questions. What I hope that you will get from this class is that you will be able to go back and say, well, why don't we try doing it this way? Whereas everybody else has just been following what they read in the literature, and it says to do it first here and then there and then there. Try it. Maybe it's good. I think you're suggesting that suppose this guy actually has poor information. He could actually make things worse over here.
Yeah, and also.
So then if this guy just operated on the fresh information. It's a probabilistic thing whether this would, whether this would work better on the average. I don't know. I suspect that once upon a time all these things have been tried, but certainly if you're in any kind of new situation, new channel, new code, you might think to try it again. It's a very reasonable suggestion. Computation is not free. There's a marked difference in turbo decoding in that you're spending a lot more time decoding each side. This BCJR algorithm is a lot more complicated than just executing, well, it's gone now, the sum product update rule for a equals or zero-sum node. That's a very simple operation. On the other hand, it doesn't get that much done. You can think of this as being, doing a lot of processing on this information over here before passing it back. Then this does a lot of processing before passing it back again. So for turbo codes, typically they only do 10 or 20 iterations. Whereas for low-density parity check codes, one does hundreds of iterations, of much simpler iterations. But in either case, you've got to deal with the fact that as you get up in the number of iterations, you are getting to the region where cycles begin to have an effect, where you are reprocessing old information as though it was new independent information. This tends to make you overconfident. It does tend to, once you get in the vicinity of a decision or of a fixed point, whether it's a decision or not, it tends to lock you into that fixed point. All right, your processing, after a while, just reinforces itself. Now, another thing, turbo codes, in contrast to low-density parity-check codes, generally have terrible minimum distance. You know, if you actually, you can work through the algebra, and, you know, there's always some weight 2 code word that produces, you know, maybe 8 things out here and 10 out here. So the total minimum distance is only 20, no matter how long the turbo code gets. All right, so when I say terrible, I don't mean 2, but I mean 20 or 30 could be a number for minimum distance. It's actually, certainly in this is called parallel concatenation, where you have these 2 codes in parallel and just pass information bits back and forth between them. It's typical that you get poor minimum distance, which eventually shows up as an error floor. In all these codes, when you draw the performance curve, as we always draw it, you tend to get what's called a waterfall region, where things behave in a sort of very steep Gaussian-like measure. When you measure distance from capacity might be, well, let's do this versus SNR norm. So capacity is always at 0 dB, and this is probability of error. So this is your distance from capacity, and this might be, you know, 1 dB or 0.3 of a dB or something very good. But then as you get down below, some cases it could be 10 to the minus 3 or 4. Some cases it could be 10 to the minus 7. So where it starts is important. Then this tends to flatten out like that. And this is simply what you get from the union-bound estimate for poor distance. So in this region, other things hurt you worse than the distance did. If you were purely limited by distance, then you'd have a performance like this. There are a very tiny number of minimum distance code words. There may be only a few in a 1,000 length blocks, so the error coefficient is very small. That's why this is way down here. The interleaver tends to give you a 1 over n effect on the error coefficient. So this is way down here, and it doesn't bother you in the waterfall region, but then at some point it becomes dominant. You can think of these as being 2 types of curve. This is the iterative decoding curve. This is simple maximum likelihood decoding when you have minimum distance of d with a small error coefficient. And so where this error floor is an important issue for turbo codes. In some communications applications, really all you're interested in is 10 to the minus 4, 10 to the minus 5, and then you really want to put all your emphasis on the waterfall region and just keep the error floor from being not too bad. So that would be a very good application for turbo code. But if, as some people think they want, error probabilities like 10 to the minus 12 or 10 to the minus 15, then a turbo code is not going to be your best candidate. All right. And it's not that you couldn't create a code with better minimum distance, but it's going to get harder. I don't know that much effort has gone into this because we have low-density parity check codes for this other application. Okay. Any questions on turbo codes? That's about all I'm going to say. Yeah?
Why not expurgate the bad code words?
Expurgate the bad code words. Well, how exactly are you going to do that?
You need memory before. It will disallow certain U sequences.
You're going to disallow certain, so you're not going to mess with the G of D, but you're going to go through, you're going to find all of the low weight, the U of Ds that lead to low weight sequences, and you're going to expurgate them. Of course, you also need to do that. It's a linear code. So if there's low weight sequence in the neighborhood of 0, then there's going to be a corresponding sequence in the neighborhood of any of the code words. So you're going to have to expurgate somehow around all the code words. I don't know how to do it.
Right.
You will sacrifice rate, right? One other thing I should mention, very commonly in turbo codes, they don't send all of these bits. They send fewer bits, which in effect raises the rate. All right, but then of course makes decoding harder because you don't get any received information from the bits that you don't send. But there are various philosophies of, it's called puncturing, that I'm certainly no expert on. And it's possible that by being very clever about puncturing, you could improve minimum, or you could do something about minimum distance. Or shortening. Shortening is where you hold some of these bits to 0 and don't send them. Puncturing means you let them go free and don't send them. So I don't know, but I don't think this is a very profitable way to go. But it's certainly a reasonable question to ask anytime that you get into a minimum distance limited situation. You should think about, is there some way I can just expurgate that small fraction of code words in the neighborhood of every code word that have bad minimum distance. Okay. This, as I said, is called parallel concatenation. Sorry, I didn't mean to cut off questions about turbo codes. I did say I'm not going to talk about them again. They've, of course, gotten a lot of publicity, are very popular. Initially, this was a revolution in coding. Turbo codes got into all the new standards and so forth. Every communications company had a small group simulating turbo codes. And so they got a tremendous amount of momentum. Low-density parity check codes really didn't get looked at till a couple of years later. As you'll see, there's a lot more analytical work you can do about low-density parity check codes, so they're popular in the academic community for that reason. But in fact, it turned out that the analysis allowed you to do fine-tuning of the design of low-density parity check codes. There are more knobs that you can do, such that you really can get closer to capacity with low-density parity check codes than with turbo codes. They have other differences in characteristics. But for both of these reasons, there's certainly a move now that low-density parity check codes seem to be the favored ones in any new standards, but we still have a lot of existing standards and people who've already developed turbo code chips and so forth who have a vested interest against moving. Perhaps analog devices is one like that. So although you can see the trend is toward low-density parity check codes, there are many industrial and competitive factors and inertia factors that they'll both be around for a long time.
And this is a patent using some turbo code. They have a patent. You have to pay royalties to a company. LDC, you don't have to.
Yeah, since this is a theoretical class, but of course issues like patents are very important. Baru, Glavia, and all were working at Ernst Britannia up in Brittany. They were funded by France Telecom. France Telecom went out and owns all the turbo code patents and has decided to enforce them. Whereas Bob Gallagher's patents all, we owned them all. We never made a dime. They all duly expired around 1980. And no one needs to worry about at least basic patents on low-density parity check codes. Of course, refinements can always be patented. So I don't know what the situation is there. And that often makes a big difference as to what people want to see standardized and used in practice. So, excellent point. All right, well, we can come back to this at any point. Serial concatenation. Here the idea is you basically go through one code, then you interleave, and then you go through another code. This is the kind of setup that I talked about back when we talked about this could be a small block code or convolutional code that you do maximum likelihood decoding on, e.g. the Viterbi algorithm. And this could be a Reed-Solomon code, and the interleaver might be in there for some kind of burst protection or to decorrelate the any memory in the channel out here. And so that's the context in which concatenated codes were originally invented, and that's the way they're used on space channel, for instance, additive white Gaussian noise channel. But here we're talking about the same block diagram, but we're talking about much simpler codes. And again, the idea is to build a big code using very simple component codes, which is what we did in low-density parity check codes. That's a big code built up basically out of zero-sum and repetition codes. Turbo code is a code built up out of two simple convolutional codes. Here, I'm going to talk about repeat accumulate codes, just because they are so simple. These were proposed by Divslar and McLeese really for the purpose of trying to find a simple enough turbo code so you could prove some theorems about it. There are hardly any theorems about turbo codes. It's all empirical. We've got now some nice analytical tools, in particular the exit chart, which was a very nice empirical engineering chart, like Bode plots and Nyquist plots, things like that. There's a real engineering flavor, but it works very well. Okay, the repeat accumulate code is basically this. We take input bits here. We repeat n times. So this, if you like, is an n1n repetition code. That's pretty simple. We have a stream. In a long block, we would then permute everything within the block. And then this is a rate 1, or 1 over 1 convolutional code called an accumulator. This is the code with transfer function 1 over 1 plus d. That means that yk plus 1 is equal to yk plus xk plus 1. So we have x coming in. Here's one delay element. Here's yk coming out. And there's what that looks like. xk plus 1, yk plus 1. Okay, so it's a very simple rate 1 convolutional encoder with feedback, where I guess we take this as the output. It's called an accumulator because if you look at it, what is yk doing? It's just, you can show that yk plus 1 is simply the sum up to k plus 1 of all the xk prime. K prime equals whatever it starts at up through k plus 1 of all the xk prime. All right? But it's nothing more than saying that g of d equals 1 over 1 plus d equals 1 plus d squared plus d. The impulse response to this is infinite, and every past xk shows up in every y. This is just the sum of all the xk's. But of course, in the binary field, it's the mod 2 sum, so it's only going to be 0 and 1. Well, it's a little two-state rate 1 convolutional code. About as simple as you can get, and obviously useless as a standalone coder. Rate 1 coders have no redundancy. They can't protect against anything. So that's the structure, which prior to turbo codes or capacity approaching codes, you would have said, what? What are we trying to achieve with this? And the reason I talk about them is that the code actually does pretty well. All right, what's its graph look like? Over here we have input bits. The input bits aren't actually part of the output in this case, so I won't draw the dongle. We just have an equal sign with n, call n equals 3, repetition from each bit. Oh, what's the overall rate of this code? Here we have a rate 1 over n code. We don't do anything to the rate here, so the overall rate is 1 over n. All right, so let's take a rate 1/3. So the graph, dot, 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 looks like something like this. And then, as always, this element, we take these bits in, we permute them in some pseudo-random permutation. And then over here, what do we have? Well, we have a trellis again. In this case, I can draw the trellis very explicitly. Here's, if we consider this to be the information bit, then to get, and this to be the previous state bit, so this is yk, say, and here's, we're considering the y's to be the output, so this is xk, I think it works either way, xk plus, let's call this xk plus 1 plus yk equals yk plus 1. So this enforces the constraint. This is really the branch. This is just to propagate the yk and present them as outputs. So this little two-state code, here's the state. The state is also the output. The state is what's in here. And this is what its trellis looks like. All right, so that's the way this looks. And of course, again, we need an equal number of sockets on this side and on this side. All right. So how would you decode this code now? What do we see initially? We initially get received data, measured intrinsic information for each of the bits that we actually send over the channel. And what's our next step? Trellis, yeah. We do the sum product algorithm on this trellis. So we just do BCJR, ignoring the fact that it's rate 1. Doesn't matter. And so we will get some information for each of these guys that we compute from the forward-backward algorithm. We'll ultimately get messages going in this direction, which come over here when we get them all. And again, from these two messages, we can compute an output message here. From these two, compute one there. From these two, we compute one there. So we combine and repropagate all these messages, and that gives us new information over here. And now, based on that, we can do BCJR again. So again, it's this left-right sort of alternation, one side, other side, which eventually spreads out the data, through the whole block. We can use all of the received data in a block to decode all the data in the block. Now, does this work as well as either of the two previous ones I put up, low-density parity check or turbo? Not quite, but it works amazingly well. This is the moral here, that even this incredibly simple code, where nothing is going on, where all we have is binary state variables. We have equals and zero-sum nodes. That's it. It's made out of the simplest possible elements. even this code can get within a dB or two of channel capacity. And I'm old enough to know that in 1993, we would have thought that was a miracle. So if this had been the first code proposed at the ICC in Geneva in 1993, and people said we can get a dB and a half from capacity, everyone would have said, you know, totally unbelievable, until they went home and simulated it. So I put this up just to illustrate the power of these ideas and where they come from. I think the key elements, of course, this idea of using the permutation as your pseudo-random element so that you, from very simple components, you get the effect of a large pseudo-random code. Could be block length 1,000, 10,000, what have you. This is absolutely key. And this basically is what Gallagher had when he said, if I just choose my parity check matrix at random, even if it's sparse, it's going to give me a random-like, which means a pretty good code. Because that's the intuition I get from Shannon and Elias. Okay, that's the important part of the code construction, but then the decoding part is this, the part of the power is the sum product algorithm used in an iterative way. The idea that you can simply let this algorithm run, and if the code is properly designed, it will eventually integrate all the information over the block and converge to some fixed point. Although, even for such a simple code as this, for this code, McLeese and his students have a few theorems and can say something about the behavior and the convergence behavior and what it's actually going to do. Even for this code, they can't get anything very definitive, I would say. So, to me, the more important thing about these are called RA codes, is that incredibly simple codes can do better than concatenation of 1,000 byte Reed-Solomon code over GF of 2 to the 10th with a 2 to the 14th state Viterbi decoder. That doesn't do as well as this crummy little thing does. Okay, so that's good to know. All right, any questions? What do we? Oh, well, it's a good stopping place. So next time, now you kind of have an impressionistic idea of how we do these codes. Next time, I'm going to analyze low-density parity check codes over the binary erasure channel, where you can do exact analysis, at least in the asymptotic case. And that will show very clearly how it is that these codes actually work. It's a good model for all the codes in general. I guess that means that you can't do a lot of the homework again. So for Wednesday, what should we do? Friday or Monday or? Monday seems to be popular. Okay, so for Wednesday, just do, there's one problem left over from problem set 8. Okay, and that's kind of a grungy problem, so, but worthwhile doing. You're trying to do the sum product algorithm at least once. So just do that for Wednesday, and then for next Monday, a week from today, problem set 9, other than that. Okay? We'll see you Wednesday.